Hey there, my name is Alejandro, and welcome back for day 33 of me doing the NeetCode 150 challenge. So today we're doing another arrays and hashing problem. Without further ado, let's get straight into it. Okay, problem 36, valid Sudoku, LeetCode medium, and seems like we've solved this already. Let's see when that was. Oh, okay, it was sometime this year, June 13th. That's about like 4 or 5 months ago. Okay, nice. All right, let's keep going. Determine if a 9x9 Sudoku board is valid. Only the filled cell need to be validated according to the following rules. Each row must contain the digits 1 to 9 without repetition. Each column must contain the digits 1 to 9 without repetition. Each of the 9 3x3 sub-boxes of the grid must contain the digits 1 to 9 without repetition. Okay, note, a Sudoku board partially filled could be valid but is not necessarily solvable. Oh, that's true, yeah. Only the filled cells that need to be validated according to the mentioned rules. Example 1, okay. Yeah, I remember, yeah, and there's a bunch of dots and so on. Okay, yeah, I did solve this a couple months ago and so on. That was one thing that tripped me up about this problem, is that I thought it was insanely difficult, right? Because I thought it's like, okay, you're given a Sudoku board and so on, and I was like, is it solvable, right? Unless, like, try and so on. I think there's a very famous, like, Sudoku solving algorithm, which is literally just backtracking, right? Then it's like, oh, you fail this case, therefore go back and so on, just keep backtracking your way until I find no solution, or otherwise, there is no solution. So I think there's even a nice number file video on that. Maybe if I find it, I can link it in the description. It's more advanced than what this problem asks, but that one is like, if you want a Sudoku solver, no matter the board, so like a board like this, it'll essentially solve you that Sudoku board, find you a solution, and otherwise probably return nothing if there is no solution, right? In this case, it's like, yeah, a Sudoku board partially filled could be valid but not necessarily solvable. So essentially, you're given a board and so on that's, partially filled, not necessarily completely filled, and you want to know if it's valid, i.e. is there any single spot that would violate the fact that this is like, a valid Sudoku board? But even though it's like, we might have like some impossible case, right? We might have like, like 1 2 3 4 5 6 7 8 9, like we might have like 1 2 3 4 5 6 7 8 9, and then it's like we might have like dot comma 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 dot dot, and like what, let's make this a dot, and then we need like 3 4 5 6 7 8 9, right? So we might have a board like this, right, where it's like, okay, obviously here the only single possible thing that we can add is a 9, right? That is the only number. But if we had a 9, this would make it like unsolvable and so on. So like this Sudoku board is actually unsolvable, but in terms of what this problem is asking, it is technically still valid, right? There is no case that is essentially like breaking the fact that like directly violating the rules of Sudoku here, right? Like here there's no duplicate numbers inside of this row, there's no duplicate numbers inside of each of the columns, and there's no duplicate numbers inside of like the 3x3s and whatever and so on. So like even though this board is not solvable, right, because by this row the only possible number you can put in is 9, but 9 is not allowed and so on, therefore there is no number you can put here, therefore the whole board cannot be solved. It is still technically a valid board, just not a solvable board. So that's essentially what this note means. And I remember, yeah, I thought this problem was way harder than what it actually was asking the first time I did it around, which I think was 2 years ago, or not like a couple months ago. But yeah, with that little clarification, this problem becomes a little simpler, right? Because essentially it's just like, step 1, check all the rows. Step 2, check all the columns. And then step 3, which I think is the hardest one, is just a little tricky. Check all the 3x3 sub-boxes, right? So essentially, like, verify that all the rows don't have any duplicates, verify that all the columns don't have any duplicates, and verify that all the boxes are valid, right? So here we can have some functions, like is valid row, self comma row, right? And maybe we get a row index, right? And here we'll do self dot board is equal to board. Here we'll do definite, self. We can also just pass board in there. There you go. We'll take in a board and a row index. And so here it's like, okay, we can use some space, right? Well, yeah, we might as well use some space, right? The point is that actually this is a 9x9 Sudoku. So this is actually going to be constant work really no matter what, right? So that makes sense. If anything, you could, you know, like go through all of Narnia and like all the possible Sudoku boards and so on, although that's probably crazily large, right? But yeah, technically this is going to be a constant time because it's always going to be 9 by 9. So the solution is probably going to be very, very fast. So yeah, okay, so here we have a board and we have a row index. Is it a valid row, right? So here we're going to do board, a row index, that's going to be a row. And here we'll say scene is equal to a set for num in row. If num is not equal to a dot, and num in scene, return false. Otherwise, we'll do scene.add num. And here we'll return true. Right? So it's like, okay, for everything in the row, it's like, okay, if we've ever seen it before, then, okay, and it's, you know, not a dot, i.e. it's a number, it's like, oh my goodness, it is definitely not valid, right? Otherwise, it's like, okay, whenever we see a number, we're just going to add that to our scene set. And then it's like, that way, it's like when we're checking, it's like, okay, have we seen that number before? And it's like, oh, if it is true, then, you know, return false. If it's not a dot, i.e. it's a number. Otherwise, I've gone through every single number in the row. None of them were duplicates. And then I return true because it isn't a valid row, right? Trickier one is going to be is valid column. So here we're going to do self board comma column index, right? So here I need to loop through every single row. So we'll have a scene set for row in board. Num is equal to row of column index. If num doesn't equal this and num in scene, then return false. Same thing, scene.add num, and then otherwise return true, right? Now, okay, def is valid sub box is valid box maybe. Self, comma, board. Maybe what do we feed in? Like, you know, the top left corner, maybe something like that. So row index, comma call index, right? So the scene is going to be equal to a set for. So we want, you know, row index, we want row index, comma call index, we want this +1, we want this +2. And then we want to do that for all of them, right? So we want this again with, you know, call index +1, +1, +1. And we want this again with column index +2. +2, +2. And so, and it's the other way around, right? So here it's like, okay, for delta column in range 2, for delta row in range 2, num is equal to board of row index, call index. Plus delta column plus delta row. Oh, we might as well switch these up, it doesn't matter. Right, so okay, now we can get rid of this comments. Okay. Yep. Num is equal to this. If num doesn't equal dot and num in scene, then we return false. Otherwise, we add that to our scene set, and here we return true, right? So now we have essentially a helper to determine if a row is valid, a column is valid, and a box is valid. And you need to feed in the indices. Okay. So here, num rows is equal to the length of board, right? And actually, it's going to be 9, right? Okay. 9 rows in total. 9 columns in total. And here in terms of boxes, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes. So 9 sub boxes in total. We'll call these boxes. Why not? Whatever. One's here. Right, so here we'll do for in range 9. Yeah, for I in range 9. Ooh. Okay, here we'll return true at the very end. If not, self dot is valid row. For row index, return false. Then here for call index in range 9, then if not, self dot is valid column of column index, return false, right? And now here let's think. We want what position? So this is 0, 0. So we want 0, 0. Then we want 0, 0 plus 1 plus 2 plus 3. So we want 0 plus 3. And we want plus 3 as well, right? 0 plus 3 plus 3. Right? And then here, actually this is the row number, right? Plus 3 plus 3. And then it's the same thing here, right? So this will be with a plus 3, a plus 3, and something here. This will be with a plus 3 plus 3. This will be with a plus 3 plus 3. With this a plus 3 plus 3. So for row index in range 0. So maybe I do 9. Okay. So I want to do 0. Maybe I do 0, 3, 6, right? 0, 1, 2, 3, 4, 5, 6. For call index in 0, 3, 6, then we're going to do if not self dot is valid box of row index, call index, then return false, right? Otherwise, at the very end, here we can delete this. Here we'll return true. So does something like this work? Whoops. Oh, they each need to have a board. Board. There you go. Okay, so something like this works. And if I submit it, let's see if it works completely. It does not. So we're failing a test case. Which test case are we failing? This is interesting, right? So this is interesting, right? Okay, 0, 3, 6. Is that not valid? We'll have 0 and 0. We'll have 0 and 3. Okay, that's not what I want. Yeah. Okay. I'll board in there. Board in there. Board in there. Is this not checking this part? Yeah, okay, so I'm not doing the 3 by 3 boxes correctly. So yeah, so I have the row index and the column index together. Interesting. What? This doesn't work? Oh, it's in range 3, but I get up to index 2, 0, 1, and 2. Okay, I'm silly right there. That is me being a little bit dumb. Okay, okay, that's a little silly mistake. Okay, so let's get rid of this. Now let's submit. Okay, there we go. Bada bing, bada boom. Working submission 95.66%. Super efficient. There we go. Okay, I wonder if we can do one thing that's a little bit better. Okay, I mean, technically it's like, you know, something like we could do is like, you know, why need two loops if you can do like, you know, for index in range 9, then it's like if not self dot is valid row board comma row index, or not self dot is valid column, you know, board of index. Okay, this is index. No, then return false, right? And then it's like you just do this and so on. So it's like there's a little bit like this doesn't even really save you anything, right? But it's like, yeah, okay, maybe like we repeat like 1 more millisecond out of it, that what you juiced up and so on. And like in here we can also like, you know, just say like instead of 0, 3, 6, so we want range from 0 to 9 with a step of 3s, right? So yeah, 9 will not be inclusive, so here we can just do like, you know, something like this. Right, so this also works. It's like here, maybe we juice out like, okay, yeah, there, we juice out a few more milliseconds out of it and so on. But again, it's just like, these are tiny like little time complexity, like O of 1 savings that like don't actually really matter, right? Where it's like the real point is like in a case like that, it's like it's silly to have these like ultra hyper optimizations, and you might as well make your code more readable, right? Where it's like step 1, it's like, oh, okay, let's validate all of the rows. Oh, step 2, let's validate. Okay, let me get rid of that extra hashtag in there and resubmit. But step 2 is like, all right, check all of the columns, right? And then like step 3 is like check all of the boxes, right? And that like makes a lot more sense, right? And there you go. Okay, so as always in all my videos, I do a quick recap of how I was able to solve the problem. So for this one, essentially all I did was just very, very simple. The very first thing to realize is that just because a Sudoku board is not necessarily solvable does not mean that it is valid. This tripped me up the very, very first time that I solved this problem. Not today, but another day before, when I solved this problem for the very first time, where it's like, just because you have something like, I think the example that I showed earlier in this video is something like, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, and here it's like, you know, pretend that you have a lot of boards here, and then the last one you have dot, comma, dot, comma, dot, comma, dot, comma, dot, 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 comma, dot, and here let's actually pretend you have the 9 and so on, and here you just have a dot. And you know what, let's add this over here. Let's just make this, you know, a proper example. So now we have 3, 4, 5, 6, 7, 8, 9. Okay, so in this example, for example, this Sudoku board is not solvable, right? So in this one, essentially, it's like you have this row. The only last possible thing that you can put here is 9, right? Otherwise, this row will be invalid. But you know, you can also not put a 9 because there's a 9 here, which would make this column invalid, right? So there's no single number that you can put inside of here, which means that this Sudoku board itself is not solvable. But in the context of this problem, this is actually a valid Sudoku board. So what they're actually asking for is there any direct violation of the rules of Sudoku in this board? Whether it is solvable or not, that does not matter, right? And the rules of Sudoku, if you're not familiar with them, is that, okay, each row must contain the digits 1 to 9 without duplicates. Each column must contain the digits 1 through 9 without duplicates. And then each 3 by 3 box, so here maybe the picture here is a little bit better, right? So this is one 3 by 3 box, here's another, here's another, here's another, here's another, another, and you can see them, you know, clearly dictated by the big black lines here, so almost like a tic-tac-toe grid, right? And so it's like each of the 3 by 3 boxes, they must have the numbers 1 through 9 uniquely. Then every row must have the numbers 1 through 9 uniquely, and every single column must have the numbers 1 through 9 uniquely, all of them without duplicates, right? And so in a case like this, the Sudoku board is not solvable, but it is technically valid because it does not directly violate any of those Sudoku constraints, which makes the problem a whole lot easier. We don't have to use, you know, an idea like backchecking to solve the problem. But in case you are curious about that, I did say I will link down below the number file video where they cover how to build a Sudoku solver with backtracking, because I think that's a pretty cool video, and in case you haven't watched it before, it's worth a watch. So otherwise, in terms of how I was able to do this, essentially it's like, okay, we're literally going to break this down into 3 steps. We're going to check if every row is valid. At any point, if we see an invalid row, we'll return false. Then if all the rows are valid, okay, let's check through all the columns. At any point, if we see that a column is invalid, then we will return false, right? And then otherwise, all the columns were valid, so let's check every single 3x3 sub box. And if any of those were invalid, we return false. Otherwise, they were all valid, which means that all the rows were valid, all the columns were valid, all the sub boxes were valid, in which case we'll return true here, right? So here you'll see it's like, okay, for every single possible row, if it is invalid, return false. For every single possible column, if it is invalid, return false. For every single possible combination, like for every single sub box inside of the problem, if it is not valid, then return false. Otherwise, everything was valid. All the rows were valid, all the columns were valid, all the boxes were valid, so we return true, right? So now let's look in terms of how did I actually implement these functions, right? And so the way that it is, essentially, it's like, okay, I have three helper methods: is valid row, is valid column, and is valid box, which is essentially take the indices that they need. So for is valid row, it just takes a row index, right? And so it's like, okay, how many row indices are there? Well, here's the first row, there's a second row, here's the third row, here's the fourth row, here's the fifth row. How many rows are there in total? Well, it's a 9x9 board, so there are 9 rows in total, right? So essentially, it's like for every single row index in range 9, right? These are the indices of the rows. Otherwise, I could, have done something like, for row in board, and then inside of here, instead of passing an index, I could have passed the board. I guess in my mind, the very first time I did this, I was just thinking in terms of indices, so I did it that way. So the same thing otherwise, right? Here is just, I say like, row is equal to board of row index, right? Same thing, essentially. Essentially, it's like, okay, out of all the 9 possible rows, I'm essentially going to pass that to my isValidRow function, but I'm going to pass its index instead of the row, right? And then with the index, I'm going to directly get the row. And then essentially what I do is, okay, what we're going to say is like, okay, we're going to keep track of a hash set, right? And this hash set is going to have at most like, 9 elements actually. Because what we're going to do is we're going to look through every single value inside of our row. All right, and for example, the first row here will have this 5, 3, 7, and these will be dots in there. So let's copy this and let's kind of do a run through of how I'm able to do it here, right? So here we have a row here, and essentially what I'm going to do is like say, okay, we're going to have our scene set, which is equal to a set, and at the very beginning it's going to have nothing, and then it's like, okay, we're going to go through every single number in the row, right? And so here it's going to be like, okay, if our scene set essentially represents the numbers that we have seen so far, right? And at any point, what we're going to do is if num is not equal to a dot, i.e. it's like, it's an actual number, like something like 5 or 3 and whatever and so on, and I have seen it before, then I'm going to return directly false, right? Otherwise, I'm going to add that to my scene set because I just saw this number. And otherwise, if for all the numbers that I've seen, none of them I had seen before, then that means there are no duplicates, and so I return true, right? And so something like this, the way it would look like is like, okay, here my scene set is here, so I start with the very first number. I have not seen it before, so I add it to my scene set and I move on. 3, have I seen it before? No, I have not, so let's add it to my scene set and let's move on. Dot, okay, we might as well add it to my scene set, that's what I'm doing. But essentially it's like, okay, the very first check that I do is if num is not equal to dot, right? There can be multiple dots and that doesn't matter, right? So if I want to return false, it must be that the num is not a dot, i.e. it's an actual number, and I have seen it before, right? So in this case, it's like when I get to this other dot, yeah, I have seen it before, but again, I'm checking for non-dots only, right? So here I add another dot, and it's like, okay, we're looking at 7. Okay, it's not a dot, and have I seen it before? Nope, I've never seen this before. So I added inside of my set here. Actually, the dots, since this is a hash set, there will be no duplicates. Dot, 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 dot. Each one that I try to add, they'll all be equal to dot, so I don't return false. So in this case, this row is actually perfectly valid, right? In this one, I don't know if any rows are invalid, so it's probably like a box that's invalid, right? I'd have to check a bit more closely. Yeah, no. Where is this invalid? Oh, that one was valid. Where is it invalid? Same as being modified to 8. Oh yeah, so yeah, for example, this sub box up at the top left, there's an 8 here, there's an 8 here, so they're duplicates, but this one doesn't have an invalid row, all right? But if I did something like 5 and 5, what this would mean is like, okay, if I start over and I see, okay, my 5 at the beginning, I've never seen it before, so I add it to my scene set, there we go. But then when I see a 5 again, it's like, okay, it is not a dot and I've seen it before, I return false. I have seen a duplicate inside of this row, so therefore I return false, right? And inside of here, it's like, oh, there's an invalid row, the entire board is wrong, right? And so I return false, right? And so that's essentially the idea. Essentially keep track of a hash set called scene to represent the numbers I have already seen inside the row up to a certain point, right? And so at the beginning I start off with an empty set because I've seen nothing, right? And as I keep seeing the numbers inside of my row, I keep adding them to the scene set, and every single time I first check, okay, have I seen this number before in my scene set, which means it exists somewhere before in my row. In that case, there is a duplicate and I return false, right? Otherwise, if I've gone through everything and I've never seen a number twice, right? For every number, it has never been the case that it was not a dot, it was a number, and that I'd seen it before, and that was never the case, then I return true, right? And essentially, the isValid column and isValid row work very, very similarly, right? So isValid column, again, scene set, and it's the same thing. It's just that, you know, I need to go through all the column indices, right? So it's like, if I look at a column like this, essentially I need to go through all the rows, and each of them, you know, only consider that column index, right? So given a column index, I'm going to look through every single row inside of the board. I'm going to only consider the number at that row's column index value, right? So for example, here, if my column is this one, I'm going to look through row 1, but I'm only going to consider this value, right? When I go through row 2, I'm only going to consider this value, right? And so that's how I'm able to look at this column. So I essentially loop through all the rows, and then for each row, given my column index, I'm going to index that row at that column index and consider that number, right? And then it's just the same operation, right? If the num is not equal to dot and I've seen it before, then I return false. Otherwise, you know, I add it to my hash set. And then if this is never triggered, then I just return true at the end because there were no duplicates, right? And then for the boxes, the very last one, a little bit trickier maybe, but essentially what I did is like, okay, if I know the top left corner index of a box, then essentially I know I just need to go like, you know, from 0, +1 or +2 is my max, you know, like column distance, or like in terms of row, it's like here, if I'm at an index 0, +1 and +2, right? So the worst case is like I go +1, +1, +1, +1, so it's like at most I'm like 2 + 2 away, right? So here I just do like, okay, essentially there are 3 possible row indices I want to consider, like, you know, here at 0, 0, 1, 0, and 2, 0, right? So it's like essentially there's 3 possible rows that I can have, 3 possible columns that I can have, and so I want to go inside of this 9x9 loop, right? So essentially it's like, you know, I just do like, you know, for DR, this means delta row in range 3, right? For DC in range 3, given the row index and column index that represents the top left of a box, I'm essentially just going to go like, okay, that row index +0, which represents this one, that row index +1, which represents this one, and row index +2, which represents this one. And then same thing for the column, right? +0 is here, +1 is here, +2 is here, right? Range 3 will actually map to, 0, 1, and 2. It will not be like 1, 2, 3, right? Just the way it's 3 not inclusive, right? And so it's like if I do +0, I'm over here, +1, I'm over here, +2, I'm over here, and same thing with the rows, right? So it's like I will essentially go through all 9 values inside this box, given that this is the top left corner, right? And so the only tricky part that remains is like, again, I just do that, and then it's like, okay, I get my num as always, like, you know, row index plus delta row, column index plus delta C. And then I just apply the very same algorithm, right? And then in terms of like, okay, the only final question that remains is like, okay, that's cool. So given the top left index of a box, I'm essentially able to tell you whether the box is valid, but I still need to find, you know, the top left indices of every single box. And so the way that is like, okay, this is an index 0, 0, this is an index 0, 3, 0, 6, right? And then here's like, okay, this is 3, 0, 3, 3, 3, 6. This is 6, 0, 6, 3, 6, 6, right? So essentially it's like, it's the very same idea as up here, but instead of like, you know, doing 0, 1, and 2, now I want to do 0, 3, and 6, right? And so one way that I essentially did at the very beginning is I essentially did like literally 0, 3, and 6 as my literal values, right? Because that way it's like, if, you know, here I'm at index 0, 0, here I'm at index 3, 0, here I'm at index 6, 0, right? Here's 6, 3, and so on. So I only want to consider the cases where row index and column index are like, you know, either 0, 3, and 6 each, and then every single permutation of those 3 numbers that they could be, right? And so a fancier way of just generating this list is just doing range 0, from 0 up to 9 and jump by 3, right? So it'll be like, you know, 0 at the beginning, then it's like jump by 3, so this will become +0 + 3, which is equal to 3. Then, okay, I'm not up to 9 yet, so jump by 3. This will become 6. And then when you try to jump by 3 and get to 9, remember, it's 9 not inclusive, right? So 9 will fail as a value. So the only ones you'll have are 0, 3, and 6, right? So it's essentially, I'm just doing the same thing as just having just the list 0, 3, and 6, but just doing a range and just using this as my skip or jump value, right? And so that's essentially all. And then otherwise, it's like, okay, that way I'm essentially able to, you know, grab every single top left corner index of every single box. And for each of those 2 corner indices, I'm going to check if the box is valid using that same helper that I had up here. And, you know, if it's not the case that it is valid, then I return false as always. Otherwise, if I've checked every single box and I've checked every single column and I've checked every single row and none of them were invalid, then it must be that they were all valid. and in that case, I returned true. And essentially, that is how I was able to solve the problem. As you can see here, it's just very, very efficient, 97.29% running time compared to other solutions. So very cool, very sexy. That's essentially how I was able to do it. So that's pretty much it for this video. As always, let's make sure that we check off the fact that we did this problem. And yeah, otherwise, that's pretty much it for this video. If you did find it useful and enjoyable, I would highly appreciate if you left a like or a comment. But otherwise, I'll catch you in the next one. So until then, ciao, ciao, my friend. Bye-bye.